Hello, everyone. Welcome to this online event of the Materials and Embodied Carbon Leaders Alliance, MECLA. Today, we're shining the MECLA spotlight on digital technologies and the crucial role they play in the pathway to net zero construction. Across the entire supply chain, from manufacturers to designers and builders, digital technologies are starting to be used to help reduce embodied carbon. And that's what we're talking about today. My name is Hudson Worsley from Precinct, and I've got the great pleasure of being the chair of MECLA and hosting today's event and panel discussion. I'm joining you today from Gadigal land of the Eora Nation, and I'd like to acknowledge that we are all on Indigenous land. I pay my respect to elders past and present, and welcome any Aboriginal and Torres Strait Islander people joining us today. Today, we will hear from a range of speakers, suppliers, designers, and engineers, addressing different technologies that they're using to achieve lower carbon outcomes. The presentations cover technologies in both the commercial and residential sectors, demonstrations on different ways digital twins can be employed, how digital modelling helps inform design decisions, and tools that engineers are using to track the embodied carbon of the projects they're working on. We'll conclude with a panel discussion and respond to comments from the audience and to delve further into the speaker's expertise. So use the questions option, the Q&A function of this webinar, to be part of that. The mechanics of today's session. We're recording the event. We have over 350 registered attendees, so welcome to everybody. And yeah, this is a webinar format, so the Q&A function is the best place to be putting your questions. I'll do my best to field questions when we get to the panel discussion, and no doubt people will be responding from their expertise in the chat and the Q&A as we go, as always seems to be the case with MECLA events. This event qualifies for 1 CPD point from the GBCA with live attendance online. So let the Secretariat know if you didn't do that when you registered. As always, I touch on the governance requirements for MECLA, MECLA members and attendees. We don't tolerate any anti-competitive behaviours. We operate in a pre-competition environment and must be aware of that. If you're aware of any conflicts of interest, speak up and we'll adjust accordingly. And remembering this is a do tank in the working for the common good. Now to business. Our discussion about digital technologies as enablers to help us reduce embodied carbon in the built environment. We have quite the panel. Our speakers today will be Richard Sood is a senior sustainability consultant at Taylor Thompson Whiting, TTW, and she'll be talking about how BIM models support her work to provide visualizations of material properties and to analyse embodied carbon. Ian McDonald, manager carbon abatement at BlueScope. He'll be talking about the digital twin the company developed for its Port Kembla Steelworks. And after MECLA's recent site visit, I can't wait to hear from Ian. Callum Prasser, a digital design project manager at Mott MacDonald. Callum will be talking to us about calculating and visualizing embodied carbon and the benefits of doing so. You might see some of his work in the digital flyer for today's event. He can talk to that when it's Callum's turn to present. Tom Petty from Grenville Architectural Constructs. He's an architect, a builder, carbon entrepreneur, who has developed an app that tracks materials that come onto site and track embodied carbon. That's exciting stuff, so we'll be hearing from Tom shortly. And Bridget Danks is a structural engineer at Arup. Bridget will talk us through the building of a database and measuring embodied carbon. She'll focus on scheme design, design embodied carbon tools, which help in the early days to compare structural components such as floor typologies, for instance. This is a fascinating lineup, so let's get started. Richard Sood, can I hand over to you as our first speaker, please?
Hi, everyone. Thanks for that, Hudson, and thank you, Alexi, as well, for organising this with us. Can everyone see my screen? We all good? Okay, I'm going to...
Not yet.
You can't.
No, not yet.
How about now?
Yes, there we go.
Perfect. Okay, yeah, so thank you very much for that. Great to be here again. I'm sure this will be another very informative MECLA Spotlight event. I'll try and do my best to live up to that expectation. So yeah, as already mentioned, I'm a senior sustainability consultant at TTW. We are a structural, civil, traffic and facade engineering consultancy. And we also have some specialist services in construction engineering, heritage, mass timber, and of course, sustainability and digital engineering. And I'm going to be focusing on the latter two today. Firstly, I thought I would begin to reiterate the challenge that we all face as built environment professionals. I'm sure most of you have heard this before, but buildings account for approximately 30% of greenhouse gas emissions globally. And in Australia, in the last couple of years, the GBCA and Think.ANZ produced a report that found that in 2019, 84% of these whole-of-life building emissions were emitted during the operation of our buildings, and 16% were embedded in their materials as embodied carbon. And they also projected these building emissions to 2050. And under business as usual, so if you continue as we are, the share of embodied carbon emissions is expected to climb to 85%. And basically over time, as the electricity grid decarbonizes and the whole of life emissions of buildings will of course come down, but the embodied carbon will become a greater percentage of a building's emissions profile. And this is because a significant share of embodied carbon emissions in buildings comes from the manufacture of building products. And they use a lot of process heat and chemical reactions that release carbon dioxide and other greenhouse gases in the atmosphere, meaning that they won't decrease by just decarbonizing the electricity grid alone. And now why us engineers and us designers should be paying attention to this, it's because the share of emissions released during the production of structural materials can increase from 8% in 2019 to up to 50.8% of total building emissions in 2050. And basically for the entire construction industry to reach net zero by 2050, which is essential to limit global warming by 1.5 degrees, we as engineers have a really big opportunity to support a significant reduction in embodied carbon emitted during the production of the materials that we specify. So to realize this opportunity at TTW, we found a lot of synergies in our digital engineering capabilities and our embodied carbon and sustainability specialties by creating a BIM-based upfront carbon calculator. We hold a lot of really useful information in our, on material properties and quantities in our BIM models, as well as our engineering analysis software, which we build quite early in the design process. And we have systems in place that ensure that we get quality and accurate data from these models. And we've also built a database of embodied carbon factors from EPDs and other Australian as well as overseas databases. And by combining these two pieces of information, so the geometry and quantities from our build models and the embodied carbon database, we can calculate the embodied carbon associated with every building that we design. And in doing this, we have created a really informative database of all of our projects. And then to effectively communicate this database and use this database, we've built a web-based reporting tool so that we can communicate embodied carbon information as informatively and in an easily accessible way as possible. And it also allows us to track the embodied carbon emissions in our projects right from the first model that we build in the early concept stages. So right from when we're starting to build our analysis models through to when we start building BIM models as we design and then finally move to construction. I don't have enough time to give you a full demo for our tool, but I will give you a snapshot of some of its applications. This is an example of the value we are gaining from linking embodied carbon data with our structural analysis software. It has allowed us to do some really quick comparisons between various column grids. And as we go through these options with the rest of the design team, through these early stages of the project lifecycle, we can really start to treat embodied carbon as a design parameter. And in this particular case, there was a distinct difference between the embodied carbon between the various grids that were under consideration. And using some of our tools to quantify embodied carbon for each of these options played a pretty significant role in decision making. And as the project progresses, we start to put more and more detail into our modeling. So once we move from structure analysis to BIM, we get more detail in our models, and therefore we also get more detail in our embodied carbon reporting. And this is an example of some of the outputs from our tools when linked with Revit or a BIM model. So the left side is a screenshot actually of our web-based reporting tool. It first applies like a standard or a conventional material specification to the concrete, steel or timber elements. And then it gives a very flexible and detailed breakdown of embodied carbon in a structure. So it breaks it down by material, by level, or by building element. So you can see how much embodied carbon is in the floors or columns or walls or foundations and so on. And we can also make adjustments to the source of each material. So we can change concrete grades, rates of reinforcement, so do some design work in the tool itself, and also then specify low carbon materials to get live feedback on the carbon implications of those decisions. Then we also link this data back to our 3D models, and we can produce heat maps like you can see on the right that perhaps maybe communicate more clearly where exactly the high emitting elements in the building are. Broadly speaking, these visualizations from our tools, what we want to focus on is how to effectively communicate embodied carbon both to our engineers so they can make better design decisions, and also back to our clients and our design teams so that we can also help them increase their understanding on the topic. So as I mentioned, our embodied carbon because we collect the embodied carbon from our BIM models, we've also been able to create a bit of a database of our projects. And this is a bit of a snapshot of the breadth of the data that we're collecting. We've collected basically, we tried to collect as many of our BIM models as possible in 2022 and ran them through our embodied carbon tool to calculate what is called an embodied carbon intensity, or the total upfront carbon emissions from the project that is divided by the gross floor area of that project. And this is the distribution of these carbon intensities across various sectors. This has really been a really great educational tool for us, as we can start to see how new projects maybe stack up against others and interrogate why some of our designs might be performing better or worse in terms of embodied carbon to others of a similar scale or similar function. And then we can feed this information back and feed all this learning back to future projects and inform the design briefs and inform effective carbon reduction pathways. And this is an example of some of the studies that we've been doing using our database. So we looked here at 5 different projects to understand the various site conditions and what the various kind of requirements of the project briefs were that led to a variation in embodied carbon. Yes, these buildings are of different sizes, but you can see like the smaller models, yes, have a lower total carbon, but sometimes can have a higher carbon intensity, which means they're not working as efficiently as possible. And then when we do these sorts of analyses, we started to realize that site constraints and the project brief can have a significant impact on embodied carbon. And we made some decisions. We were able to kind of take some of these learnings from these studies and put them back into new projects. And the studies have really also shown us how important site selection is when it comes to embodied carbon. And we're starting to ask, are we building the right building in the right site? And to help us answer these questions, we've also plugged in our carbon tool to our planning and analysis tool. And this tool basically overlays overshadowing and sun access planes in Sydney and Melbourne, the CBDs, to automate building massing and yield estimates, and also automates some building layouts. This is a very high level introduction to this tool. I'm also not the best person to talk about it because I'm not a planning expert, but it's also quite unusual for an engineer to have something like this, but this is in no way trying to replace a detailed feasibility study. But we are doing this here because it allows us to provide embodied carbon estimates from the structural components. Considering they make up such a large proportion of a whole building emissions, it helps us to make assessments on which sites would be best suited for a low carbon structure and achieve similar yields. And basically, to summarize the huge amount of information that I've just given you, there are many opportunities for embodied carbon reduction along the life cycle of a project. And our tools are really focused on trying to unlock as much of that potential as possible. And then by linking carbon with things like our planning tool, our structure analysis software, our BIM models, it allows us to inform benchmarks, to inform reduction targets, do quick calculations and comparisons to come up with really effective reduction strategies unique to each project. And using these different types of visualizations allows us to also communicate these opportunities in an accessible way. And most importantly, I think linking embodied carbon with digital technologies has allowed us to focus on reducing the quantity of the material in the structure to reduce embodied carbon before we even go down the path of using a low carbon material specification. So just to end with a bit of a shameless plug, I guess, our tool sets and research and all of our embodied carbon advice on projects are all motivated by our commitment to reducing upfront carbon. We've committed to reducing carbon in our designs by 50% by 2030. And we've measured all of our projects completed in 2022, as I mentioned earlier, and this forms kind of our baseline from where we are going to reduce from as a company. And we definitely wouldn't have been able to get to this point without using digital technologies. By interrogating the materials in our BIM models and by doing comparative analyses, as I've shown you today, we're not only advising on our projects on reduction strategies, but we're also learning from them ourselves in order to reach our own targets. And I think the most recent IPCC report that came out a few days ago has really reinforced for us that we need to cut greenhouse emissions quickly and sharply and in this next decade. And I think it's the argument to put embodied carbon in the too hard basket is kind of diminishing, and especially with the growing amount of data that we have and the tool sets that are available to us to measure embodied carbon. And I mean, for TTW, yes, our designs aren't technically part of our carbon footprint, but we also have the skills and the expertise to make a really positive contribution. And the use of digital technologies to create accessible and educational visualizations really helping us to move in the right direction. So yeah, that's it from me. I'll hand back, but please feel free to reach out anytime, and happy to answer any questions in the chat or later on in this discussion.
Thank you, Richard. Look, setting the scene there, as you did with the research from GBCA and ThinkStep, was fantastic. And then tying it back to the urgency expressed by the IPCC. I do a lot of work on climate risk assessment, and people say, oh, is the science changing much? And I say, well, the main thing that's changing is the level of confidence and the certainty of what's going on, not the direction. And so, yeah, sheeting back to why we're doing this is so important. The point that embodied carbon is too hard, yeah, I think the momentum that MECLA is building up and the number of organisations for whom it's of interest shows us that no, it is hard. But boy, we can really make some big changes. Fascinating to hear that you couldn't do what you're doing without the digital technology. So with that in mind, let's move on to our next speaker. But thank you, Richard. I look forward to coming back to you in the panel discussion. Ian McDonald from BlueScope, Manager Carbon Abatement. If I could ask you to pop on your video and audio. Really looking forward to hearing how you apply digital technologies to the very real world of steel making. Thank you, Ian. Over to you.
Yeah, thanks, Hudson, and thanks very much for the opportunity to present today. I guess moving on from what Richard was talking about, one of the big embodied carbons is the input materials, including steel. So I'll just try and share my screen. Give me a second. Oops.
That's working, just not on presentation mode yet.
Okay, no worries. Yeah, so again, thank you for the opportunity. So my name's Ian McDonald. I'm the manager of carbon abatement. I've got a fairly interesting but difficult task of trying to decarbonising our steelmaking facilities, both here and abroad, in Australia and abroad. But the focus, and to be honest, BlueScope's biggest focus is on the Port Kembla Steelworks. So the Port Kembla Steelworks, it's an integrated steelworks, and integrated is the key word there, in that it's very complicated. There's different process units that interact with each other. So a saving in one area might not necessarily mean a saving overall. So yeah, it's an integrated steelworks that uses virgin iron ore, coal and other raw materials to produce steel slabs, hot rolled coil and plate, and then downstream into other building materials as well. So steel is acknowledged as a hard to abate industry, and that's due to its capital intensity. It's very intensive, capital intensive. It has very long-lived assets that last 20, 30, 40 years. So one of the big concerns is, say, China, which has increased its steel output dramatically. A lot of those assets have many years to run. And at the moment, there's unfortunately limited commercial alternatives for greenhouse gas intensive production technologies like the blast furnace route at Port Kembla. So we thought one of the ways to assist us was to develop a mass and energy balance, a digital twin, to evaluate greenhouse gas abatement options, including projects, different raw materials, things like that. So we went ahead and did that, which I'll get to in a couple of slides' time. I'll actually present it. Yeah, so we developed the digital twin using site data and operating procedures with a company called ICD, who are now Transfield. And we used AnyLogic software. So the model's been validated with 4 years of greenhouse gas data, and the main parameters are well under 5%, so 1 to 2%, which is pretty good. Just a bit of a background too. So previously we had Microsoft Excel models that were very complicated. There was only a limited number of people who understood them. And the problems were they were complex and time consuming to modify. So typically someone would come up with an idea and we'd have to wait a week or two to come back and say, yeah, that works or that doesn't work. The other big problem was that it used annual averages rather than a range of process conditions. So the graph I've got there is actually the blue line is the actual measured coke ovens gas data. So coke ovens gas is one of our internally generated gases that we use as a fuel source. And as you can see, it's very non-linear. So the coders at ICD came up with the orange line, which is a model that sort of mimics that to some extent. But you can see how inappropriate an average number would be for that particular parameter. Yeah, and the Excel, we did make some errors with Excel, and one of the big ones, which is probably not ones we thought of, but the calculations weren't documented. So now we've got a functional design spec of this model, so we can go back and say, okay, that's the way it works, and change things accordingly. Okay. I'll just move on to the model. Wonder if people can see that. I hope they can. Yeah, so this is the landing page for the model. So second. Yeah, so it's got about 100 different parameters that go into the model. There's the main parameters, which for us is hot metal tons. So that's the production out of the blast furnace, the amount of scrap we use. So the more scrap we use, the lower the greenhouse gas intensity, and some various others. But if you look, have the different parameters, there's plenty of other parameters. You can see all the carbon emission factors here. Fortunately, it is a bit slow at the moment. Other parameters, you're going to add a whole new set there as well. So there's about 100 different parameters we can sort of modify. There's two different versions to this model too. There's a single mode, which is the one I'm looking at now, and there's a batch mode where we can run 8 different models at once. Given it's a little bit slow, I'll just go back to the landing page. Something happens with these kind of things, technology. Start again. So I'll just press go. So basically it runs a year's worth of data. So that number's the amount of minutes in a year. So it might be very hard to see on your screens, but you can see this is the sort of, we call it a GUI, a graphical user interface that looks at the different input and output streams. And you can see by the number of interactions, there's lots of processes that are interlinked. So each line has a carbon emission. So it's got a mass flow, so tons of iron ore or tons of limestone or dolomite, and how much carbon emissions goes into that. And it's a live model, so you can speed it up or slow it down. So basically a 1-to-1. So for every second is 1 minute. So times 5 is 5 minutes is 1 second. And I can speed it up to as fast as I like, or slow it down, or whatever I want. So I'll just run it flat out. Yeah, so there's all sorts of different landing places we can look at. It's modifying as we go along. But I guess the key point for us is we can change the parameters to see what the effect of the steel carbon intensity, which is probably one of the inputs to some of the materials that certainly is an input to some of the materials used downstream. Yeah, and we can look at individual units too to see what's happening at, say, the blast furnace or the coke ovens or other things like that. So this area is all about our internal gas use, which is pretty critical. So there's interesting interactions where sometimes you might think an option like using more scrap it also has a downside in that we have to use more energy elsewhere. So it sort of quantifies that. Yep. Okay, I won't tempt fate by changing anything else, but I just thought I'd give an overview of the digital twin model. It has been used in anger in a few scenarios. One of the best outcomes was actually we were about to install a new turbo alternator to generate more electricity, and there was a big argument of whether there was enough gas to power that. And this basically made it look better than we expected. So that was a positive. Okay, thanks very much.
Thank you, Ian. That's terrific. I was actually going to ask you when we get to the panel question, what type of decision do you use this to help in, what decisions do you are informed by the use of this tool? So love to unpack that a bit more, but I can see that 4 years of data gives you a pretty good starting point, and then tweaking the variables. I like the GUI. I think graphical user interface, having been taken around the steelworks by your colleagues to actually see, okay, well, if you change this, the knock-on is throughout the plant. And yes, integrated, we'll get you to talk a bit more about that too, what that means, that the off-gas from one process becomes an input for another. That was fascinating to see. Thank you, Ian. Let's come back to the panel discussion a little bit later. All right, our next speaker is Callum Prasser from Mott MacDonald, Principal Design Project Manager. Can I get you to turn on your camera and microphone?
Yeah, I think Alexi might have to turn on my camera.
Okay.
Because I'm unable to.
The puppet master behind the scenes.
But I'll share my screen. Yep, there we go.
And this is another take on a digital twin type tool. So over to you. Thanks, Callum.
All right, thanks very much. Okay, just let me know once you can see that.
Yes, nice and clear.
Okay, great. Okay, so my name's Callum. I work at Mott MacDonald Engineering Consultancy, and specifically in a team called the Extended Reality team, which sort of looks after like 3D modeling and visualization. Today, I'm going to talk to you about one of our platforms that we've developed called the Carbon Twin, and how we've used it for visualizing and calculating embodied carbon. There'll be a few things that I touch on that are similar to what the first two speakers have discussed, but then hopefully get to a point where you can kind of see how our tool is used slightly differently, particularly from an engagement point of view. So just to start at the beginning, the Carbon Twin started life as a pilot project and also a collaboration across 3 business units at Mott MacDonald: Digital Advisory, Extended Reality, and Net Zero, since all 3 teams shared some common goals. And as an engineering consultancy, Mott MacDonald has the ability to influence carbon impact, particularly through the design phase. So this partnership would enable us to leverage some unique skills that we have within the company across software development, computational design, and visualization to develop a carbon tool to enable more informed decision-making for our clients and projects. Here's just an image of the 3D model of one of the projects that we've used as a case study. So we identified this project because it had detailed BIM assets. This is the Kidston Pumped Hydro. It's located in North Queensland and was designed in partnership with GHD. And Mott MacDonald were responsible for the structural components. The pumped hydro itself is operated by Genex Power and is the first of its kind in Australia for over 40 years. The Kidston site also includes a large solar farm and a future wind farm facility. So from this point of view, it's a really fascinating test case when we consider embodied carbon at the portfolio level. And for an energy asset like Kidston Pumped Hydro, which has developed digital models, there's 2 primary opportunities that we saw for the Carbon Twin. The first is to unlock emission reduction opportunities, so retroactively assessing carbon impacts in their existing facilities and identifying areas for improvement in future projects. And then with this knowledge, we could deploy the platform on future projects and design for net zero emissions by incorporating carbon considerations early in that design process to ensure asset investments align with strategic roadmaps and transitions to net zero. Therefore, the key question we asked from the beginning was, can we calculate embodied carbon retroactively and in an automated way? And also, can it be displayed in ways which are both engaging and informative? Because this is one of the key things, I guess, about getting the message out and increasing people's comprehension levels. And then also, how do we link BIM assets to Mott MacDonald's Moata Carbon Portal? So this is one of our own proprietary platforms that we have deployed on a lot of projects, and in what ways can we deploy and communicate the data? So just to give a bit more background, because I think it's important to understand how some of these products and platforms come to life. We looked at the platform requirements more detailed and defined the problem, which was essentially the need for efficient tracking and visibility of embodied carbon to enable collaboration and decision-making. And then some of the key tasks that we aimed to solve was, how do we link material quantities and BIM assets calculate and interrogate embodied carbon intensity, and enhance carbon 3D data through visualization. And then thinking about a market fit, we've narrowed our focus just to the sustainability and energy management sector for the time being, and divided our target users into two groups: the doers, such as the consultants, engineers, or facility managers, and stakeholders like executives, government, regulators, and the community. And then this formed a two-part and two-platform approach to the carbon twin: the carbon dashboard and the carbon visualizer. So both complementary products that appeal to different audiences and users that I'll take you through. So firstly, with the carbon dashboard, it sets up the framework and the automation processes to calculate embodied carbon. This is just a brief overview of the workflow that's implemented to create the framework for the carbon twin. So in its basic form, it involves configuring the source data, that being a Revit model or IFC model, running the embodied carbon calculation, and federating the model for integration into a dashboard. I just touched on this quickly because it's important to understand it's kind of the type of parameters and metadata that needs to be available in some of these digital design models in order to calculate embodied carbon. So like, for example, to start with, we require two key parameters in the source Revit model, which are the material type and element volume, highlighted here on screen. And then the next step involves matching the carbon values with the Revit elements using Mott MacDonald's Moata Carbon Portal, which is essentially a material database, and running a script to create the energy analysis values within the model. Then once that's all complete, it's ready for export and federating in the cloud for the dashboard. And this is just a quick video of the finished dashboard. So allows visualization of the carbon information. You can see a cost slider for carbon pricing at the top of the screen, other information. There's a window to interact with the 3D model and filter by design packages or materials, and then also select individual elements and turn on a heat mapping visualization setting to show intensity hotspots. So the benefit of this kind of dashboard, that's lightweight, it's quick to implement, and has a bit of more of a technical and data focus, which is useful for some technical users. Then part two involves taking the foundations and the data that underpins the carbon dashboard to create the carbon visualizer, which is more for enhancing the content for engagement. So the visualizer is built on the Unity gaming engine, which some of you might be familiar with. The basic workflow includes ingesting various types of 3D data into the Unity editor, creating the 3D environment and the interaction and functionality, then building the platform into an exe file for deployment. So I'll launch that later on and show you some of the things within it. We can then also capture other content from the platform, as well as deploy it to other devices for VR and AR applications. And then, as part of this process, to streamline our workflow a little bit further, we developed an automated process of populating models and UI elements with carbon values from the dashboard. So this toolbox that we created to create the platform is designed to streamline the creation of new 3D scenes for the visualizer, making it easier for developers to iterate and produce custom scenes for any facility, but also it enables a faster implementation of this type of platform for our clients. And the step-by-step process takes developers through setting up a facility, importing the BIM model, adding the interactions, linking the data, and then generating the build. So while the visualizer shares similar benefits with the dashboard that I showed before, we found that the rich visualization side of it, which is accurately modeled and integrated in context, has the ability to aid the comprehension of embodied carbon across a broad range of users. You can then also create a lot of value when you overlay this kind of visuals with real data and define a clear use case scenario with purpose. Some of these combined benefits are captured in this snapshot from the platform that shows the engineering model integrated in context, immersive environmental conditions, simple navigation system, and an interactive menu with embodied carbon data and tools. So aside from the 3D interactivity and automated data integration aspects of the platform, there are a number of other key features included within the Carbon Visualizer. So I'll just run through a few of these. And in order to do so, I'm going to just launch the platform itself. So I've got quite a powerful laptop here at home, so I'm able to launch that very quickly, but you can kind of see it's a very detailed environmental 3D model, and then you can kind of easily navigate through the different facilities at Kidston and sort of click on a carbon intensity graph and understand the material makeup, jump between different assets within the portfolio, the solar farm and also the wind farm over here. And then you can jump back to some of the key locations using this navigation map in the bottom corner here. And then you can open up the menu. You can enter like a carbon cost, just saying indicatively I've added there. And then that populates out information across your portfolio, but also within Kidston Pumped Hydro, and then specific elements, which you can kind of drill down into further. So I'll jump down into the powerhouse main cavern and transformer cavern. It's located underground. I'll just turn that menu off. A feature we've built in is to make this a bit more easy to see within the model as you zoom in and out, and kind of the casing around the powerhouse kind of pulls away. And then once you click on that specific element, you can also isolate that, similar to what you saw on the dashboard. Turn on the carbon heat mapping tool, and then also review the carbon intensity within that element. In terms of other functionality, we've got a few different animation settings in order to sort of simulate operations within a facility. So I'll just turn off this and I'll zoom out. Here we've kind of animated the water level changes between the two reservoirs and also the volume. And you can kind of play with those settings and turn them on and off and the values. And we've also got other performance and sort of interaction and help settings to help users guide their way through. So it's really easy for anyone just to jump in.
2 more minutes, Callum, just on timing.
Yep, no worries. I'll just exit that. And that's back in my presentation. So I'll just jump to the last slide. I had some videos presented, but I thought I'd just fire up the actual platform. Cool, so where can we go to with this? So just some things to finish on. The success of the carbon twin has led us to consider some opportunities to develop the technology into a more integrated offering. So some of the areas where we think the carbon twin platform has the potential to involve include, for the dashboard, integration into a Revit toolbar, then also sustainability assessment tool integrations, which I know a number of like major infrastructure departments have these kind of tools as part of their projects. And then also for the visualizer, creating a carbon comparison tool so you can compare across portfolios and industry benchmarks, generating an automated carbon report out of the platform so you can share and communicate easily, and then integrate with other systems for operational carbon emissions. So yeah, just a few things to finish on to think of, and that's it. Thanks very much.
Callum, thank you. I can see I'm not an engineer, and as a non-technical person, I can see that visualization suddenly makes it look very real. It actually made me think of a PlayStation 4 Star Wars game that I play with my kids, but the idea that you can visualize and show the hotspots, the heat map, that's fantastic. So really looking forward to hearing that drawn out in the panel discussion. But thank you for showing that and using the power of your laptop at home. Fantastic. All right, stay online for the panel discussion a little bit later. Next, we have Tom Petty. Tom, can I get you to turn on your camera and microphone? G'day, mate.
All right. G'day all.
Thank you for dialing in. Residential housing, residential building and construction. Take it away. Over to you.
Thanks very much, Hudson. Thanks to all. It's I feel like I'm the other end of the spectrum here. I'd probably describe myself as a carbon nerd with a tool belt. I have a small company, Grenville Architectural Construction. We build one-off architectural homes, and I've been down the carbon rabbit hole for some years now. So I just thought I'd touch on why I started looking at it, and the little app that I've developed, and sort of what I'm working on now. So yeah, we build one-off homes. It's myself and 3 carpenters working down in Melbourne. So very small scale, interesting projects. And I thought, all right, I want to try and get behind this carbon idea. How can I measure the carbon that's in my projects? So I integrated sort of carbon optimizing into my tendering system, so I could theoretically output, this is how much slab I think is going to be involved in the job, and therefore here's the footprint. Can we reduce this, and then talk to the project team and the architects and so forth. And that was all well and good. People, looked me up and down and sort of weren't quite sure what to make of it. But at the end of the day, I didn't have any way to really validate the accuracy of these calculators. So I thought I need a way to actually measure stuff that's arriving on site rather than using like theoretical bill of quantities stuff. So I developed this little app, and it's not as sexy as any of the other stuff we've seen today. But there it is, just little me. So I developed an app where I could basically log every delivery that arrived on site. It automatically assigned an embodied footprint to that delivery, accumulated in the cloud, and then I could draw down a summary number of the project, which I then put on a digital sign that was on the front of the building. So this is a real site that we worked on, and this is our sign, so forth. So this little app, you'd plug in, project summary of what it was. You'd plug in what the material that was arriving was. It would load the CO2 factor. You'd basically put in how much was on the truck. You'd take a photo of the delivery docket so you could archive that and have transparency. It would load it up and allocate it, so you'd start to see a breakdown within a project of what was actually delivered. And you could also see each file, each uploaded docket, so that for auditing purposes, in theory, you could trace back everything and see how you arrived at that footprint. Pretty rude animal. The output was this sign with a number on it, basically, and we had a QR code so we could see who was looking at it. And it was sort of the public aspect of it was really where it's sort of started to mean something. The takeaway from the app was that the real benefit was in these carbon conversations that we had as a result of this digital live sign. The site was down the road from the pub, so we had all the punters, coming in and saying, "What's this all about?" The subbies were like, "Oh, what's this mean?" And those conversations were really, paradoxically, the best bit of the whole exercise. I found the number itself almost entirely meaningless to everyone, including me, mainly because we had no comparison, no relativity. Was it a good number or not? And the process of actually manually entering each delivery docket, photographing and so forth was, quite labour intensive. Fundamentally, while the client and the architect were interested in it, it wasn't integrated into the process at all. And great for carbon nerds, but it sort of missed picking up anyone else for the ride in a way, which I think was a real shortfall of it. And fundamentally, we were building what was already designed. We did have an optimization process where we took down the footprint by about 30 tonnes, but it was a case of, that's cool, but it's already documented, it's already engineered, we can't change it, just build it. So it was far too late in the process to actually make a difference, although, as I said, the conversations that came off the back of it was a real benefit. So kind of jumped through to sort of last year where I thought, how can I do better than that app? And it really came down to getting the clients empowered with knowledge. How can a environmentally conscious client have informed decisions about what implications their design and their material selections will have on their footprint? And how can they be a part of the process and help drive change up the entire chain? And that is the building process chain: client, designer, specifier, builder, supplier. How can everyone be interconnected? Because if we're not all kind of getting behind this, it's all well and good for each little sector to be drilling down into it. But if the others aren't coming along, it's always going to be hogtied by that the person pulling the least weight. I also realized that the footprint number is actually not very interesting compared to a quantified number of actual savings that can be achieved. So the discussion shouldn't be, oh, the slab's 50 tonnes. It should be, you could save 10 tonnes if you change the slab design. Or if you change the fly ash, you could save 15 tonnes. That, I think, is a much more useful mechanism to get clients on board. So you don't have to understand an LCA study and all the pitfalls of that to say, oh, okay, well, yeah, I want to make a low impact building. That sounds good. That was what sort of drove this, as well as trying to connect everyone in the build process together to really get behind or be a part of what is essentially a carbon ecosystem. So by this connection process, what I'm talking about is a client is able to make informed decisions based on numerical data, not just theoretical, we've got a green product, use this. Actual numbers was what was important to me. That means the designer needs to be equipped with carbon optimizing calculators that, while they themselves may not fully be down the rabbit hole, they should have access to tools that they can deploy at early stage, not at late stage. And it shouldn't necessarily involve another consultant. Sort of accessing a wider market means you need to have spec-ready templates so you can pick a supplier or a process and have them easily dropped into the contract. So then that allows suppliers who might have a low carbon product to tap into the designer and the client market directly, where they've got this quantified low carbon outcome, rather than trying to compete on price with a builder who would otherwise just pick the lowest price. Fundamentally, the builder has got too much on their plate to do carbon, in the way it really needs to be done. Even I ran out of steam on this a bit, so got to be super simple for the builder. It can't be another process. It can't be another whole engagement or cost. So how can this thing run in the background and accumulate data in an automatic way? So connect all these dots, and so this is real data. I'm basically at the stage where there's wireframe back end that's been stitched together. Not very sexy Excel, mea culpa, but that's just little me. And I'm kind of trying to get the back end all tied together so that I can get a front end. If it looks like I can build a narrative, can then put it all together. But this is a real job. This demonstrated the savings that were achieved where we nominated a low carbon alternative and just tracking some data. The designer portal might look something like this. This is the real calculator. It's sort of like a Richa at the start. It's the little year 6, my first website version of that, I suppose. Excel, it's me and a few different foundation systems. And if you put in a few known simple concepts at the start, what the ultimate looks like, the footprint could look like. So these sorts of really simple early stage stuff that just plant the seed and idea, as well as connectivity to EPDs from local suppliers that can get fed into that, is sort of that exists now. I've spoken to some of my suppliers. This is, I think, the way invoicing is going to look down the track. There's no reason why we can't scrape the type of material and the quantity information off the already digital dispatch dockets that are zooming around, leave off dollars, just look at quantity and stuff and have that accumulate back a house. This is the manual process I was talking about before that should and can be automated. And that's sort of what I'm working on. But from a supplier point of view, to be able to offer something like this to a market that is ready within an ecosystem which has a space for it, is I definitely think the future of material dispatch dockets. From a builder's point of view, the theory is you'll have this access to this live number, which is great for company image as well as that conversation point of view and engagement with the public. And then summary values, which you might use if you're going for Green Star accreditation on Portland cement reduction, for example. This would automatically spit out kind of where you are. But the essence, it's a one-click carbon report. So carbon trace, look, I mean, it is little me. I have to say, MECLA Hudson's charisma and enthusiasm has really what's kept me going these years, because it is an amazing organisation and concept that they're driving. So they've been amazing in just moral support. But I am deploying this carbon trace on some of my work in the next couple of projects to see that it means something. And then at the same time, I'm trying to find people that I can develop this with, as well as talk to the key players in industry, so engineers, architects, suppliers, and other builders, to see how is this valuable? How can this be useful? How can this not be so complicated? Because I think that's a big setback at the moment. So that's me, that's Carbon Trace. Thank you all again.
Brilliant, Tom. Thank you. And stop apologising for it being simple. I think communication theory 101 says know your audience and you must pitch to them. And so the highly sophisticated McDonald model that went before you, a different audience. You're wanting to talk to tradies, suppliers, and residential architects. I don't think it's horses for courses. So that's fantastic. And judging by some of the comments in the Q&A, I think have a look at that if you're wanting to know whether you're on a worthy mission, because there's quite a lot of interest there. Keen to have you come back into the panel discussion after we hear from our next and final speaker. So stay online. Thank you, Tom. Bridget Danks from Arup. You've spoken at one of our earlier events. Thank you for that. And very keen to hear from you again this time. Can I hand over to you, please?
Yes, sure. I will share my screen.
That's working. Great. Thank you.
Okay, great. So hi, everyone. My name's Bridget, and I'm currently on Wurundjeri Woi-wurrung country. So I'd like to acknowledge the Wurundjeri people as the traditional owners and thank them for having me on their land and for their ongoing care for the land. So my presentation today is about a couple of the digital technologies that we've developed at Arup for use during the scheme design stage. Yeah, just echoing what Hudson's just said, it's been so great to see all the different variety of tools that are happening in different sectors of the industry. So next slide. These are just some similar stats to what Richard showed at the beginning, which I included just to set the scene because I'm a structural engineer in the buildings team at Arup, which means that my team has a large role to play in the overall embodied carbon of the building. So in this example, in the pie chart, the structure makes up 65% of the building's embodied carbon. And this is for a typical commercial office building in the UK. So this is a great graph from WBCSD's recent publication, which I'd really recommend having a flick through. It's really well presented and very interesting. On the vertical axis is degree of impact of design decisions on embodied carbon, and the horizontal axis shows the level of specificity of the design aspect. So the tools I'll be presenting today focus on these design elements. And ultimately, these design aspects are decided on at the brief or scheme design stage. So that's where we've been really focusing recently with our design tools, because this is where we as design structural engineers have the greatest potential for impact. We can make key design decisions that have a big reduction in the embodied carbon of the structure. So the two tools I'm presenting today are the embodied carbon comparator and the pathways to reduction diagrams. And actually, these are both really great for understanding that relativity of embodied carbon for different design schemes, which, Tom, I can really emphasize that it can be hard to have that perspective when you're just starting out with embodied carbon calculations. So first, onto the embodied carbon comparator. So this is currently housed in Excel, although we're looking to move it into parametric in the future. And essentially, the screen I'm showing you here, it's divided into your input on the left-hand side and your output on the right-hand side. And in your input, you get to define 3 cases for your structural typology for your floor plate. So here you choose your floor type. It might be concrete, steel, CLT, a combination of multiple. The next option is just how in-depth you want your calculations to be. Maybe we'll just keep it simple for now and say no to these options. Here you define your span. So here we're looking at a 6x9 grid. You define your loads, number of floors, floor to floor height, and your materials. There's also a couple more input options that are below this screenshot. And you run the comparator, and what you get in your output is the total embodied carbon per square meter for your building. And it also shows you the reduction compared to your base case, or maybe an increase compared to your base case. And you can also see a comparison of your foundation loads, your base shear, and this is the summary of the design for each option. So it's estimated the slab depth, the beam sizes, and the column sizes for each of those 3 options. So I'll run you through a demo now. What I showed you just before was 3 different material types, but maybe we've decided to go for PT, a post-tensioned structural typology system. So let's change them all to PT. And then instead of a 6x9 grid, maybe we'll have a 9x9 grid. Oh dear, my battery's about to die. It's really bad timing. I don't know why that's working. Let's see how long I last. You can also have a 12x9 grid. We'll just see how these compare. So now I'm going to run the comparator. And you can see that comparison 1 had a 9% reduction, which is great, but 12x9 grid, not great. It's got an 11% increase. So let's go back to a 9x9 grid, but maybe we can alter something else. We'll increase the cement replacement from 50% to 60%. And we run the comparator again, and we've increased our reduction to 15% from 9%. So that's a quick demonstration of how quick it is to get a bit of a feel for the impact of certain design decisions. So the second tool that I'm presenting is our pathways to reduction diagrams. So this we developed, the idea was we wanted it super simple, like an A3 page that you can print out, carry into meetings with the client or others from the industry, so that we can all get a better idea of which options we have for reducing embodied carbon. So we've got 3 stars, so to speak. Top left is concrete, top right is steel, and the bottom is timber. And each arrow coming out from the center is what we call a lever, a design attribute which you can vary to modify the embodied carbon. And the stronger levers are represented with a thicker arrow. So let's see. Oh no.
Is your battery gone, Bridget? All right, I think we've lost Bridget there. Alexi, can you bring the screen back? Terrific. All right, it wouldn't be a live webinar without at least one technical hitch. So that's our technical hitch for the session. That was a fascinating tool, and I'm really hoping that Bridget can find a power cable, plug in and join us. But I might ask the other speakers, Tom, Richard, Callum and Ian, to turn your cameras on and your microphones on. I'm hoping you might also have access to look at the questions, because as ever, the MECLA audience is very active, very engaged and asking some probing questions. I might start going through them because, yeah, they're a fantastic place to start. But thank you all very much. I think it is clear we've got deep technical data outputs from BlueScope. Ian, I can just see the level of detail there is amazing, but also in an integrated works that is highly complex with massive inputs and outputs. So fit for purpose. The other bookend being Tom, your Excel, which is still more detailed than I could ever deal with. So good on you. But fit for purpose also. Can I ask, coming back to Richard, with your first presentation, one of the questions that came up, you were looking at big structural elements, but what about fit out? Is that in your remit? Is it in the tools capability, or is that later in the design process?
I guess short answer is no, we're not capturing fit out.
Yep.
So what we model is predominantly structural materials. So the kind of the so what's above ground and below ground as well. So
yep.
Superstructure and substructure. And we're quite lucky in that we've been modeling it in a lot of detail for quite some time, and is just part of our documentation. And we're also quite lucky in that they're the easier parts of a BIM model to quantify in terms of material quantities. And there is, yes, a big kind of challenge for the rest of the materials in terms of finishes and some fixings to get to the same level. But I think Bridget also touched on this at the start of her presentation, in that the structure is such a large proportion of the emissions that come from a building. And I think to kind of capture the low-hanging fruit, it's really important to consider. I find a lot of the time we kind of get really stuck into trying to measure every single part of the building, which is, yes, important in terms of carbon accounting. But at the end of the day, I think we need to remember that it is about reduction and where we can make the biggest impact. Yeah,
bang for buck. I noted that star in the quadrant that Bridget had up about, which was essentially bang for buck. Where do you get your biggest impact? Can I ask about data sources? Where do you each get your factors from? Tom, let's start simple. You've got metrics for how many 100 kilograms of cement are coming on board. How do you come up with the metric for the carbon intensity of that?
So it's pretty dumb from my end. I have found the two low carbon suppliers working in Melbourne, which is Wholesome and Boral, and they have EPDs available. And I use those EPDs when I specify the load that gets delivered. And that's it.
That's it. Yeah, makes sense. Callum, when you're doing the carbon component, obviously many dimensions of design can be analysed, the variables examined in that tool, but where do you get your carbon factors from?
I mentioned during the talk that McDonald have a platform called the myriad Carbon Portal, which is essentially like a materials database. So we draw upon data information from that. Then it's also kind of a case-by-case basis with the actual digital like Revit models that we deal with, and either seeing if they have that information already, or if they don't, getting it up to a standard where we can use them for our platform.
Okay, thank you. Ian, can I ask you that question? And Bridget, if you're there, maybe pop on your camera and microphone. We're in the panel discussion now.
Yes,
I guess
my
my carbon factors are a lot easier. I get their scope 1 and 2, so they're not embodied carbon. So they come from the National Greenhouse Gas and Energy Reporting System. So it's fairly standard. But
all right. And while we're going around the room, Bridget, the carbon factors that you use when testing the variables, where do you go for that data?
We're currently using the EPIC database from the University of Melbourne because it's open source and publicly available, but that data is hybrid data instead of process data. So we're currently looking to transition to a process data database.
Okay, interesting. Yes, and our working group 2 on measurement has obviously spent a lot of time looking at those alternative data sets and process or input output. So, okay, that's interesting applications in the real world. Those of you talking BIM, do you want to just, for the general audience, what does BIM stand for?
Building information modeling.
Great, good. Just don't want to get stuck in an alphabet soup of acronyms, so that's good. the BIM modeling, how does that deal with non-typical materials? A good question in the online. So membranes or something that's not a ton of concrete. How do you come up with a factor for that? Maybe Richard to start with.
Sure. Yeah, those things are tricky because you don't typically model the extents of those some membranes on a BIM model, but you can sometimes extract, like if you have a surface, you can extract the top surface area of that surface, and if you know there's a membrane on that, you can extract kind of the area of the membrane and get a quantity for that. So yeah, those things are, they can be, but the details from a BIM model can be very tricky.
Okay, Bridget, do you have a experience with that as well?
Sorry, I was distracted by the chat. What was the question?
Question around how does, when you're using BIM modeling, how do you address non-typical material, something that's, you know, not from, oh, we'll just draw it from the database. How do you come up with a meaningful input so that you get a quality output?
Yeah, that's definitely something we've been thinking more about, because we want to have that consistency about the assumptions we're using. So if you pull an EPD just for one material, you know, particularly because EPDs tend to be derived using the process driven method as opposed to hybrid, then it's a bit incompatible using that with our EPIC database that is hybrid. So yeah, I guess as much as possible, trying to have consistency in at least the process through which the carbon factor was derived.
Okay, interesting.
Could I also, sorry, I had to just weigh in on
go.
thinking on the coefficients, which have been sort of the start of the rabbit hole for me. I think it's probably fair to say no one will ever really agree on any coefficient. And so if they remain dynamic value that can be modified, hopefully improved upon and compared using the same tool, providing that's the same, if it's process, it's the same typology, I think it's easy for that to distract the whole conversation. And actually what's important is not the number that some people have said is the right one, but it's how it's being applied. And that's why I think all these tools.
I was interested in your point, Tom, when you said it's not the number, it's the saving that resonates with decision makers. Can you talk more to that? Because I suppose that reinforces that point that 80-20 is good enough, because it's actually about, you know, what aren't we using rather than the second decimal place of what we are using.
That's right. I mean, I think it's, again, residential's maybe its own world because there aren't BIM models. It's largely these, you know, tens of thousands of houses being put up with slab on ground and not much thought applied to anything. So if you focus on the biggest bang for buck, which is concrete in a residential sector, how can you just use that? And there's a question in there from Joe on the reference case you would apply. And I guess there are a few structural solutions that would be more or less commonplace. And I guess if you nominate a starting point and nominate an accepted baseline coefficient, and then can talk to these other low carbon options, and also talk to maybe more expensive foundation system, but where you can actually identify what those savings are, it means more to the end user, I think, if it's just a mum and dad, than it does to say really getting the conversation too complicated. I guess I'm coming from the dumb end of the market in a way.
Yeah. Well, I'm dumb in that case because I like hearing it at that high level and conceptual chunks. That makes a lot of sense. One of the key themes I'm hearing from all of you, though, is that this is about communication, that you're taking complexity and then putting it into a language or a visual that decision makers can use to inform what they need to do. Ian, I'm keen to hear from you examples of where it's changed what you do because you've got this digital twin.
Yeah, I guess one of the big things is speed of looking at different things. So as I mentioned in previous really simple Excel models, it takes weeks or several weeks to look at a different project. I guess in terms of tangible outcomes, I mentioned, one of our projects that we're about to install is a new turbo alternator to generate more electricity from our indigenous gas, we call it. So we actually made the decision based on the Excel model, and then we rechecked it later, and it made the case look a lot better, which gave us the confidence to go forward. So I guess the other thing that's happening right at the moment is, it's topical, is the safeguard mechanism that's in the news, and certainly we're using the digital model to sort of assess the outcomes of that.
Yeah. Well, that's very topical and very very impactful. Thank you, Ian. Callum, can I come to you? Yours really, you mentioned having, I suppose, a gaming software company involved in the development of that tool, and that was evident in just the richness of the graphics. How does what you're doing influence design decisions? What changes are made because the decision maker can see that rich visual representation of their options?
Yeah, I think when it comes to what we're trying to achieve is that often the decision makers are not the people with the tools who are designing, or not always with the technical know-how. So I think sometimes like being able to visualize things like the way we've done it kind of cuts through the noise a little bit, gets people's attention, enables them to be part of the conversation, or something maybe they might not otherwise have much input into. So yeah, I think it's trying to create a bit of a level playing field from a understanding of embodied carbon point of view.
Okay, that's a good answer. One of the comments in the chat is saying, look, and I've said it's not the number, it's the change, pointing out that actually the numbers are important for organisations that are having to report on Scope 3 emissions. Getting an accurate number does matter, and yes, point taken. That's a very good point. A question from our mate Joe Carton to Bridget. Does the tool pull in smarts from the circular buildings toolkit to also test for the ongoing adaptability or flexibility, circularity of particular structural floor or element types? Question for you, Bridget.
I think that's a really great question, because that's something that we really want to have more of a focus on in the future within my team, like thinking about circular economy, because other parts of our have been working on circular economy, but certainly within our team, we've been a lot more focused on embodied carbon. And I think over the coming decades, like circular economy is a big ticket item. And the answer is at the moment, no, our tools don't incorporate that sort of thing. And part of the reason is the tools I've presented today are really high level scheme design, like very broad brush strokes. We're not talking details of like floor finishes and that sort of thing. But certainly in terms of circular economy, things like disassembly of primary structural elements is very relevant. So it's definitely a really interesting area that needs more attention, and we'd like to focus on that more in the future.
And I can feel there's clearly a trend there, Bridget, that moving from upfront and embedded to whole of life and circularity. A couple of the questions are asking that type of thing. Well, what about after it's been built? So yeah, that's bang on topic. One of the questions is actually to MECLA, which I might answer about. All of the tools today presented have their own pros and cons. This is from Ben George. Do you think it's about time MECLA makes its own version of software to track emissions? The answer to that is no, because we're not resourced and don't have the, we're not planning to be an ongoing entity like a Green Building Council or an Infrastructure Sustainability Council. It's very nice that we're being asked, but the budget, the resourcing, the skill sets, that's not what MECLA is wanting to do. There are many tools, and I don't really want to get into being a competitive entity that's doing that. Bringing people to have these conversations, to put forward the solutions that our five speakers today are discussing. That's what MECLA is here to do. If we identify the need for that, for another tool or a central database, for instance, that's something we would very much advocate for. but another tool into the market, I don't think will be where MECLA goes. Do any of you have questions for each other? I know we've got a couple of structural engineers at the table, well, 3 of you. Detail from the very hairy end of industrialization, making steel as fundamental as it gets for our built environment. Tom, have you always wanted to ask a question of BlueScope and never had the chance?
Gee whiz. Yeah, I need a bit more time for that, I reckon.
All right. Look, I'm trying to say it's not just me
Yeah.
asking questions to you. What would the panel like to ask of each other or ask of the audience?
I'd be sorry if I could jump in before you, Callum. I'd be interested in seeing how engineers and architects, like that's typically a similar relationship to builders and architects, reading between the lines. What is the sort of receptiveness back upstream or downstream of your tools?
I'm happy to start. I guess from our end, it's been mostly positive, but it can be mixed. You know, with our tools, we're able to get in if we're engaged early enough. When we're kind of going through different schemes, we can give quite quick kind of indications of the embodied carbon of different designs. So I think typically design teams have been quite receptive to that, but also, you know, there is a challenge between, you know, this, for example, if you're going to reduce a column grid, there's a spatial implication of that. So it is about kind of having those discussions really early on, so everyone kind of has their input and we find the best solution for the project. And it's just embodied carbon is just it just needs to be looked at one part of the whole process. But yeah, typically we're getting pretty good feedback and reception from our tools up to this moment.
Richard, we might, I felt for you with your battery running out just as you are on live national television. How about, can we come back to you for your last couple of minutes, give you a chance to wrap up what you were saying?
Yes, thank you. And sorry about that, everyone. I've got a
Not
new
at all.
laptop, and I'm not quite used to.
All good, no stress at all.
Okay. So I was just about at the end anyway. I'm assuming you can see my screen now.
These are terrific diagrams. They've got a lot of complementary points in the chat, by the way. I think everybody really love these. So please tell us more about them.
I think the simplicity of them is what really appeals to people, really making it a lot more palatable, these discussions. So the next thing I was going to show you was the way that we've actually automated them so that they're adaptable. So this is done in Rhino and using Grasshopper. And so if I just start this video, so we can first have a look at what levers there are more specifically. We've got concrete strength, slag percentage replacement, reducing your grid. You can choose different floor systems and also different floor loading if you have the capacity to reduce that. And similar levers for your steel floor system. And for timber, you can vary floor loading, the grade of your timber or the grids. So now, unfortunately, in the video, you can't see it, but there's a CSV file that's being modified, and that's to change which levers are being included in the star diagrams. So they've just pushed that change through, and now we also have an additional lever arm for fly ash. So that's an example of how the star diagrams can be varied. And in the timber star diagram, they added the floor systems to the timber star diagram. The other thing that you can change is the increments at which you vary one of those levers. So initially we had 25% increments of your cement replacement, but now we've just toggled that. And now instead of 25% increments, it's 10, 30, 60, 80% increments. Yeah, so that was actually the end of my presentation. I just added a slide at the end here. This was also from the WBCSD publication. So yeah, it's a pretty motivational statement for the built environment. 2030 is today, because buildings commonly take 5 years to build, or maybe 7. And if we expect to have the embodied carbon emissions by 2030, that means that the buildings we're designing today need to have a 50% embodied carbon reduction. And as we saw in the embodied carbon comparator tool, the first tool I showed, a lot of those changes that I was making only had a 10 to 20% embodied carbon reduction. So we need to do more than just 1 or 2 small changes. We need to make bold design decisions to commit to that 50% embodied carbon reduction in our buildings. And understanding the different levers we can pull to reach this is so important. So yeah, I really love MECLA because I feel like it's really motivating. It's nice to see what everyone else is doing in the industry, but let's make it happen today. And yeah, definitely let's keep communicating, because I think collaboration is not only productive, but essential if we're going to meet these like bold targets that we really need to meet. So, yeah.
Terrific. Thank you, Bridget. And I'm glad we got to see your wrap up there. We are nearly at time. I want 1 bullet point each from our panelists to wrap up. What's next? You've shown us what you're doing now, and that's some of it's new, some of it's, for Tom, it's early stages for Resi, but, can you tell us what's your next thing to drive the reduction in embodied carbon in your part of the built environment?
Concrete. I reckon residential, it starts with concrete.
Yeah.
It's a low-hanging fruit. We've got to get onto fly ash. People have to understand it's not a compromise. People think it's just concrete that's been fluffed up with rubbish. And that change is communicated through all the subbies.
All right. While I ask the others, I want you to have a look at the chat and the questions, because there are quite a few people interested in your dumb tool that ain't so dumb. So have a look at that. Ian, what's next for you?
Yeah, I guess the model can increase in scope. So we can, I showed what we call upstream. So that's before metal coating, painting and cold rolling. So it's increasing the scope. We have considered what I call scope 3, I guess, which is interesting to you guys as well. One thing I should say we definitely won't be doing with this model is put cost in. So that's something that a lot of people asked to put in, but that makes things a lot more difficult. So I'll just focus on carbon with this one.
Yeah. Okay. Keep going. We want green steel here in Australia. So great stuff. Thank you. Callum, what's next for you and Mott MacDonald and the use of these amazing visualization tools?
Yeah, so there's been a few comments around investments and sort of, you mentioned with MECLA, that'd be very hard to do these kind of tools with the resources you have available. The reality is, even with like a relatively large company like Mott MacDonald, a lot of these kind of things are done off the back of like the smell of an oily rag. So I think our goal would be to get a few more projects under our belt where we can sort of implement this tool, develop it further, and start sort of, I guess, cataloging some of the achievements and goals that we want to hit with it and for our clients.
Okay.
And just become more normalized within our workflow.
Yep. That touches to one of the last questions in the chat, actually, about engineers to mainstream this design software to make it affordable, because in this case, small regional councils don't have the resources, the funding to pay for the big end of town to do its really expensive, sophisticated stuff. Would be great if that gets mainstreamed into business as usual design. Richa, what's new? What's next for you?
I guess maybe this question, I'm not answering what's next. It's kind of what we're currently doing and hoping to continue do.
Yep.
I think there's a real risk with some of these tools when you get rubbish in and rubbish out. So a training on what we're actually inputting into tools and how to actually read the outputs, I think is really important. And we've been, over the last 6 months, kind of doing a big education push in our teams, and kind of pausing on some of the developments and kind of more focusing on how to use the information correctly.
And that's a very such an important thing. Rubbish in, rubbish out is a risk of any human system. So, yep, that makes a lot of sense. Bridget, final word to you. What's next? And it might be more of the same. And please do keep doing more of the same. What's next for you?
I would say, you know, we've got the tools now. Now we just really need to use them. And I don't think it's, you know, the urgency is really here, and it's not about mucking around, thinking yes or no. We need to make these quick comparisons on day one of the project, get everyone in the room together to commit to what percentage reduction we want to make on the project. And yeah, so I'd just echo what Rich is saying, like really need to make sure that everyone's along on the journey, not just one or two people in the team or the company. Yeah, to really make this happen on every project.
Fantastic. All that's left for me to do is to say thank you to our terrific speakers today. I think hearing from you working in the field in this evolving area of expertise within construction, within manufacturing and within engineering, it's brilliant. Richard Sood from TTW, Ian McDonald from BlueScope, Callum Prasser from Mott McDonald, Tom Preddy from GA Construct, and Bridget Danks from Arup. Thank you all so much for committing time and effort and a little bit of stress to today's presentations. Really appreciate that. Thank you for joining in exposing yourself, being vulnerable in questions. Never know what's going to be thrown your way, so thank you for that. Really terrific presentations, which will be recorded, which are being recorded and will be uploaded onto the MECLA website with a link sent to email to all the registered attendees. So thank you, guys. As ever, I want to thank Monica Richter, Project Director for MECLA from WWF. Her positivity and determination are just instrumental in the success of MECLA's mission. So thanks, Monica. To Kati Vahayan and Alexi Barnstone. Alexi, particularly behind the scenes with today's webinar from Climate Kick. You guys make the Secretariat succeed, and your strategic insights and observations as we go always add to what we're doing. To everybody, please keep an eye out on our socials, keep it on particularly LinkedIn for updates and relevant industry happenings. We've got our ever-growing body of resources. Today adds to that. And yeah, look, our national reach increases. We're talking increasingly to governments around the country, Western Australia, Queensland, Victoria, New South Wales, all in a reciprocating, you're doing it, let's do more. Can we help each other? It's great to be part of this. Thank you for all of your contributions. Stay tuned for our next event. Keep you guessing what that might be. Keep an eye on our channels. Really look forward to seeing you. For now, that's it. Thanks, everybody. Thanks a lot. Thanks, panelists.